Hey guys, how's it going? Mr. Mitchell here. In this video we're going to go over 3 worked examples to show you how to do problems involving escape velocity. Now if you haven't already done so, check out my previous video covering the theory on this topic, and that way you can apply what you learned in that video to this one. So let's get started. Question 1 says to calculate the escape velocity from the surface of the Earth for part A. So writing down what we know from the question, we're trying to find the escape velocity v escape. We know that g is 6.67 times 10 to the minus 11 meters cubed per kilogram per second squared. The mass of the Earth is 6.0 times 10 to the 24 kilograms from the datasheet, and the radius of the Earth is 6.4 times 10 to the 6 meters, also from the datasheet. So writing down our equation for escape velocity, we have v escape equals the square root of 2gm over r. Putting in our numbers now, we get the square root of 2 times 6.67 times 10 to the minus 11 times 6.0 times 10 to the 24 divided by 6.4 times 10 to the 6. If you put all that into your calculator with the square root, it will give you an answer of 1.12 times 10 to the 4 meters per second. Or another way of saying this is about 11.2 kilometers per second, which we saw in the theory video. Part B says to calculate the escape velocity from the surface of Mars, and I've given you some Mars data here. So the mass of Mars is 6.4 times 10 to the 23 kilograms, and the radius of Mars is 3.4 times 10 to the 6 meters, because you don't get that on the datasheet in the exam. So we're trying to find escape velocity. We know that g is 6.67 times 10 to the minus 11 meters cubed per kilogram per second squared. The mass of Mars is 6.4 times 10 to the 23 kilograms as given above, and the radius r is 3.4 times 10 to the 6 meters. So writing down our equation, we have v escape equals the square root of 2gm over r. Putting in the numbers now, we get square root of 2 times 6.67 times 10 to the minus 11 times 6.4 times 10 to the 23 divided by 3.4 times 10 to the 6. And if you put all that into your calculator, we should get an answer of 5.01 times 10 to the 3 meters per second, or about 5 kilometers per second. Which makes sense because we're saying that the escape velocity from the surface of Mars is less than half that from the surface of the Earth, and the reason will be because the gravitational field strength on Mars is a lot smaller than the gravitational field strength on the Earth. So it's common sense to think that the smaller the gravitational field strength on that planet, the smaller the escape velocity will need to be for that object to escape the planet's gravitational pull. Question 2 says that in the Apollo space missions to the moon, the spacecraft was in orbit around the Earth at a height of 185 kilometers before it headed for the moon. Calculate the escape velocity from this orbit. Well, writing down what we know from the question, we're trying to find the escape velocity. We know that g is 6.67 times 10 to the minus 11 meters cubed per kilogram per second squared. The mass of the Earth is 6.0 times 10 to the 24 kilograms from the datasheet. The distance r this time is the radius of the Earth plus 185 kilometers. So putting in our radius of the Earth from the datasheet, we have 6.4 times 10 to the 6 plus 185 times 10 to the 3 for the kilometers part, and putting that into your calculator gives 6.59 times 10 to the 6 meters. Writing down our equation now, we get v escape equals the square root of 2gm over r. Putting in our numbers, we get the square root of 2 times 6.67 times 10 to the minus 11 times 6.0 times 10 to the 24 divided by 6.59 times 10 to the 6, and if you put all that into your calculator, you should get an answer of 1.10 times 10 to the 4 meters per second, i.e. about 11 kilometers per second. So if it was on the surface of the Earth, we saw in question 1a that it would be 11.2 kilometers per second, but because this spacecraft was already at a height of 185 kilometers above the Earth's surface, it doesn't take as much velocity for that planet to leave the gravitational pull. So that wins about 11.0 kilometers per second. Lastly, question 3 says that the escape velocity from the surface of the moon is 2.4 times 10 to the 3 meters per second. An object is projected from the surface of the moon with a speed of 2.0 times 10 to the 3 meters per second, and we're told that the mass of the moon is 7.3 times 10 to the 22 kilograms, and that the radius of the moon is 1.7 times 10 to the 6 meters, because those won't be given on the datasheet. Part A says, will the object escape the moon's gravitational field? Well, to answer this, all we need to do is look at the two speeds and simply compare them. So we've got our object speed there and our escape velocity there. So the answer to this is no, since the object's speed is less than the escape velocity from the moon's surface. Part B says to calculate the maximum height reached above the moon's surface. To do this, we first need to find r and then subtract the radius of the moon to find the height. So writing down what we know from the question, we're trying to find r, and the velocity which we use here in place of the escape velocity is the velocity of the object, v equals 2.0 times 10 to the 3 meters per second. G is 6.67 times 10 to the minus 11 meters cubed per kilogram per second squared. The mass of the moon is 7.3 times 10 to the 22 kilograms, And writing down our equation, we have v equals the square root of 2gm over r, and again we're going to use our velocity of our object instead of the escape velocity, which is why I've dropped the subscript of ESC, escape. So putting in our numbers, we have 2.0 times 10 to the 3 is equal to the square root of 2 times 6.67 times 10 to the minus 11 times 7.3 times 10 to the 22 divided by r. Squaring both sides now to get rid of this square root term on the right hand side, we get 4 times 10 to the 6 equals 9.74 times 10 to the 12 divided by r, where all I've done there is multiply all of these terms together on the numerator. We can then cross multiply by r to get it over to the left hand side, and that's the same as just swapping this term and this term here. So we end up with r equals this term divided by this term, and that gives us an answer of 2.43 times 10 to the 6 meters. However, we're not finished though, because we want to find the height of the object above the moon's surface. So remember, what we need to do now is take our r value and subtract the radius of the moon. So we get 2.43 times 10 to the 6 minus rm, and putting in our numbers now, we get 2.43 times 10 to the 6 minus 1.7 times 10 to the 6 from the question, which gives us a final answer of 7.3 times 10 to the 5 meters. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video one of these, subscribe, and I'll see you in the next one. Take care.